Welcome to ECON 3406. My name is Mike Sinke, and I have taught Stats 2 for a number of years, although I have to be honest, this is only the second time that I've taught Stats 2 in the middle of a pandemic, so the basic features of this course are the same, but we are going to alter a little bit of what we do based on COVID-19, like everyone else has. Stats 2 is a bridge to being able to do quantitative analysis for an entry level business position. So we take what you've learned in Stats 1, which is a lot, and we review some concepts that you've learned, which you may not remember or may not have learned that well the first time. And we add some new concepts that we hope will enable you to feel competent to do some analysis for a business should it be the case that you need to. And my encouragement to all of you who are in this class is just to have an open mind about the possibility of doing these things in the future. So even though you may not be of the mindset that you're ever going to use any of this stuff again, the last 6 months should have made it abundantly clear to everyone that we don't exactly know what the future holds. And as a consequence, I think we should just be open-minded about the fact that, hey, some of this stuff that I'm learning now, it really may be valuable in the future. And so I want to start by reviewing some essential components of Econ 3402 that I think everybody should have learned in either Dr. Lee's or Dr. Bolt's or Dr. Patron's or Dr. Lopez's Stats 1 class, or even if you took it from me a while ago. But if we didn't learn these things, then we can learn them today. The first is called the mean. I'm only focusing on the arithmetic mean in this class, although we do know that there is a geometric mean. For the mean, you add up all of the data points in a data set and you divide by n. N is the number of data points. So n is a description, it's a count. And so let's just say I have 4 data points like the third bullet point here. The data points are 1, 2, 3, and 6. Well, I add them all up. 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 6 is 12. I divide by n is 4 to get a mean of 3. Now that mean of 3 is a description of where we think the center of the data set is, and it is constructed from all the values in the data set. So it's not the only possible measure of location that we could have. You may remember the median from Stats 1, but we're going to be using the mean routinely in this class, so we're going to keep the impact of those outlying data points in our data set. The standard deviation is an important measure of dispersion, and we denote it as S sub x, standard deviation of the random variable x. Now, I'm treating this as a sample standard deviation here. So we do know that there's a difference between the sample and the population, but most of the time when we're collecting data from a sample, so I'm going to be speaking primarily in this class about sample data. And we'll be using terms like the sample standard deviation or the sample mean, understanding that there is a population mean and that there is a population standard deviation. Let's unpack this formula. Take a look at the second bullet point. You see a square root sign over everything in the formula. To the left of this sigma, which is a summation sign, we have 1 over n minus 1. So it's a fraction. This value is going to be less than 1. The summation sign is a sigma. It's a big sigma. So it's an instruction that tells you to add. It tells you to add something specific. It tells you to add everything after the sigma. You can see that the sigma is an instruction telling me to add from I equal 1 to n. I is a description of the data. So it tells us the identity of the data points, and it just says, hey, start with the first data point, which is 1. It doesn't matter what the order of the data points is, just any order is fine. Just start with the first one and go all the way to the last one, the nth data point. So we start with the first data point. We're going to perform this operation that's after, and we're going to do this for each data point all the way until the last data point, the n data point, which is 4. N is 4. So we have 4 data points here, and we're going to perform this task for all 4 data points, and then we're going to add it up. So let's try it out. That's this 4th bullet point here. Xi is the data, okay, and it's our sample. We take each data point and subtract the mean, which we found. X bar is the sample mean. We square it. So the first data point is 1. I subtract the sample mean, which is 3. That's -2. I square it. That's 4. I do the same task for the second data point. The second data point is 2. I subtract the sample mean, which is 3, and I get a -1. I square it, that's 1. I do it for the third data point, which is 3. 3 minus 3 is 0. 0 squared, still 0. I do it for the fourth data point. The value is 6. 6 minus 3, 3. Squared, 9. I add them all together, 4 plus 1 plus 0 plus 9. I get 14. Now, 14 is the sum of squared deviations of x from its mean. I divide by 3, which is the same as multiplying by 1 over n minus 1. So I take 1/3 multiplied by 14, and I take the square root of that to get 2.16. 2.16 is a description of roughly where to look for the data in relation to the mean. So it tells us kind of an area where most of the data should be relative to the mean. So we measure distance from the mean in terms of standard deviations, and those standard deviations are going to provide some region for us where most of the data will lie. Okay, the reason we start by immediately introducing the mean and standard deviation, which are concepts you learned in Econ 3402, is because they're essential to modeling probability, and they're essential components of a hypothesis test. So in Econ 3402, you learned a number of different ways to model probability. You learned some counting methods, combinations, permutations. You count the number of outcomes. You have a Venn diagram to model some unstructured probabilities. You did the binomial distribution. You had means and standard deviations of random variables. You did this with discrete distributions. In Econ 3406, we're going to focus on one special continuous distribution, the normal distribution, where we can't count the number of outcomes. So how many numbers are between 1 and 2? Well, as many as you want. That's a continuous distribution, but if I were to pull a number out of that interval randomly, I wouldn't be able to count the number of outcomes. And I think modeling probability is one of the key problem-solving tasks that you learn in Econ 3402. So we all model probability informally every day of our life. So I try to evaluate how likely good outcomes are to occur, normal outcomes are to occur, and bad outcomes are to occur. That modeling, those modeling choices guide almost all the decisions that I make because the future is uncertain. So consider commuting to West Georgia. I choose the route based on how quickly I'll get there, but also how safe it is. So I may not want to take the windiest road imaginable. I may want something that I'm more familiar with because I'm trying to reduce the probability of a bad outcome and increase the probability of a good outcome. And we've seen this firsthand during the COVID-19 pandemic. So modeling where spikes will be is critically important for saving lives. So modeling when a state will run out of ICU beds or the probability that utilization will increase rapidly is important to saving lives. It has been the major sort of touchstone of policy discussion in the last few months, and it's a probability question. And we look at mean outcomes and standard deviation of outcomes in modeling probability, and those are key components of the normal distribution, which is the distribution we're going to look at for kind of reviewing probability in this class. So all of these probability distributions I just talked about are good ways to model uncertain outcomes depending on the situation that you're in, but we're only going to use one as a review for ECON 3406, and that's the normal distribution, the bell curve that you saw with the z-scores in Stats 1. There's a strong theoretical basis to focus on the normal distribution, which is called the central limit theorem. So one of the reasons every single stats class on the planet harps on the normal distribution is because there are some strong reasons to actually do that. And the central limit theorem, what it does is says, hey, look, you have a population, take a sample of size n, and keep sampling sample sizes of size n. So we're just going to take a sample of 10, and we keep sampling size 10 over and over again, or whatever the sample size is. Now that population has a mean mu and it has a variance sigma squared. The variance is the standard deviation squared. Now take the sample average of those samples that you just took, call it x bar. Here's the key point. As we sample more people, as n gets larger, so we go from 10 to 20 to 30 to 40, and we look at the sample average, the distance between the sample average and the true mean mu approaches 0. So xn here is the sample mean for a sample size of size n minus mu, that's the true mean, whatever that is. That distance approaches 0 as n gets really, really large. And we call this z here. Z is the description of this variable that's made, and this is a standard normal distribution. So I don't expect anybody to remember any of the components of the central limit theorem or what it does. What I want us to focus on is that this is a big deal. The underlying population doesn't have to be normal. We could just keep sampling from it, take the sample averages, and the distance between that sample average and the mean is going to be 0, regardless of if I just had a population of zeros and ones, which clearly isn't normal, or if I had a population that was uniform, or if I had a population that I like rolling a die, looking at the sums, any of those things, it won't matter. As I sample more, the distance between the sample average and the true mean is 0, and the standard deviation is 1. And it will be normally distributed. So if I sample enough people, I can appeal to the central limit theorem and just call that distribution normal without it being a huge improper statistical jump. And so in Stats 1, what we did is we just focused a lot on the z-score as a method of converting distributions to something that was standard normal. So we used the z a lot in Stats 1, but we actually had sufficient reason to do so. And so the normal distribution models a large range of data sets, but we're really interested from a Stats 2 perspective in its capacity to model random samples. So random samples are how we get information about the world around us. I don't know very much about the world around me. How do I learn? I gather data. Do I pick the data points that I want? No, I gather randomly. And how do I analyze that data? I can use a normal distribution. So what we do is we model many random samples as being normal, and then we evaluate probabilities associated with those samples using a standard normal distribution with a mean 0 and standard deviation of 1. So, if you take a look at the average number of minutes that somebody watches these YouTube videos for Stats 2, well, it ain't 0. Okay, the minute you click, the clock starts. Do I know what the distribution of minutes looks like? Is it exactly normal? No, but maybe I can model by randomly sampling some of the students. I can get a sample mean and I can calculate a sample standard deviation. I just go back to these previous slides and I do the same technique that we had on those slides. Okay, well, maybe I want to find the likelihood that somebody watches these videos for at least 10 minutes. I don't have a table for the YouTube video minutes. I'm just learning based on the information that I just gathered how long the sample average that I see is, but maybe I can convert it to the standard normal distribution and go from that anyway. Okay, so let's backtrack. What are some facts about the normal distribution that are important? The first is that the probability of a single number is 0. It's continuous. Any number you can think of is on a bell curve. It's symmetric. It's single peaked. The mean and the median are in the center. Now, where do the standard deviations come in? Well, no matter what the mean is, 68% of the data points are within 1 standard deviation of the mean. 95% are within 2, 99.7 are within 3, roughly. And so you end up with something that looks like this. Now, here is a standard normal distribution where the mean is 0 and standard deviation is 1. 68% of the data are within 1 standard deviation of the mean. So it's pretty close to 3/4. And even if you go back to this very small sample, look, the mean is 3. 1, 2, and 3 are all within a standard deviation of 3. Only 6 is within 2 standard deviations. And that's completely consistent with this picture where 3 of the 4 data points in that example were within 1 standard deviation of the mean, and the last data point was within 2. We would expect that. We expect most of the data to be within 2 standard deviations of the mean, regardless of what the mean is and regardless of what the standard deviation is. So x is the variable, and height represents probability here. Okay, so let's try to look at an example of when we used the normal distribution in Stats 1 and try to work ourselves back into some problems that we're familiar with. So let's just take a look at the time it takes to cook dinner. Now, I cook dinner a lot. In the pandemic, it takes different amounts of time to cook dinner because I have a 3-year-old son and a 22-month-old daughter. And sometimes they're pretty good about dinner, and other times they're harassing me while I'm making dinner, and they're clinging to my legs and yelling at me, telling me to turn Bluey on. I don't know if you're familiar with Bluey, but apparently it is a show on Disney Junior that involves a blue talking dog from Australia, and my kids discovered it and love it and are harassing me while I'm cooking dinner. So sometimes it takes longer to cook dinner than 50 minutes, and sometimes it takes less time than 50 minutes, and there's a standard deviation associated with that. And let's just say it's 15 minutes. So it's very, very unlikely that I'll get dinner done in 20 minutes or fewer, but it's also unlikely that I'll take an hour and a half to make dinner. It's going to be in that range. Let's pretend it's normally distributed. So x is a random variable, and that's the amount of time it takes to cook dinner, but we're pretending that it's normally distributed. This tilde implies normal. N for normal, mean of 50, standard deviation of 15. Okay, so about 2/3 of the time it'll take me between 35 and 65 minutes to cook dinner, and 95% of the time it'll take between 20 and 80 minutes, and 99.7% of the time it takes between 5 and 95 minutes. That's the assumption we're making. Okay, so this is a description, a modeled description of how long it takes to cook dinner. I do not actually collect the data for how long it takes to cook dinner, and I have not actually verified to see whether it's normal, but it's an assumption I'm making, and I appealed to the central limit theorem to do it. So when we solve problems associated with this, the plan is to change the time it takes to cook dinner into the graph on this previous slide where instead of having a mean of 50, we have a mean of 0, and instead of having a standard deviation of 15, our standard deviation is 1. So the idea is to recenter this cooking time into something we're very familiar with, which is the z-table. We do that by calculating a z-score. So z changes x into a variable that is centered at 0 with standard deviation of 1. So it's a conversion. Think of it as a map. Okay, so let's say I want to know the probability that it takes an hour or more to cook dinner. X is 60 minutes. The mean is 50, mu. The standard deviation is 15. So I just make a z-score using the z formula. 60 is x, 50 is the known mean, 15 is the known standard deviation. So I have 10 over 15, which is 2/3, about 0.67. And let me show it to you on the next slide. It's about here. Now, more than 60 is this area in red. Area in red. So it's to the right of 0. 2/3 is closer to 1 than it is to 0. And I'm looking for an area to the right. What do I use the z-score for? So I converted 60 minutes to a z-score of 2/3, but 2/3 is not a probability. It is a rescaled location of 60 minutes. So what I want to do is use that 2/3, use that 0.67 in some way to find this probability. Okay, so let's say I want to look up the probability of an hour or more. I'm going to use the 2/3 in some way, and I'm going to use it with what's called a z-table. The z-table is a very extensive chart of probabilities. It is a probability of less than. So all the z-table does is provide us areas in blue. Now you'll note that I want the area in red, but all the z-table provides for us are the areas in blue. That's okay, because if you're not in the blue, you're in the red. So I know that if I want an area in the red, I just have to take 1 and subtract the area in the blue. But let's use the z-table to look up 0.67 so we can find the area in blue. Okay, so how do I use the z-table? Here is my z-score, 0.67. The rows of the z-table, this is important, correspond to the 10th place of the z-score. So I go to row here, 0.6. Why 0.6? Because 0.6 is the 10th place. Now I go to the columns next. Columns correspond to the 100th place. Each z-score is rounded to 2 decimal places. So the 100th place is a 7. Okay, so I'm in row 0.6, column 0.07, and I look at this area here, 0.7486. Okay, and you can see it right there. Row 0.6, column 0.07. Okay, so the probability of getting a z less than 0.67 is 0.7486. That's this area in blue. What if I want the area in red? That's what it said in the problem. So I wanted the problem to know the probability of taking an hour or more to cook dinner. Okay? I subtract from 1. 100% of the time, it's going to take me some amount of time to cook dinner. It's either 60 minutes or more, or less than 60 minutes. So we looked up the less than. That's what the Z table reports. But we need to subtract from 1 to find the probability of greater than. You can think of this, if you're trying to apply what you learned in Stats 1, as the complement rule. Either it's less than 60 or 60 minutes or longer, and those are the only two possibilities. Well, it took me 27 minutes. Great, that's less than 60. Well, it took me maybe 85 minutes. Great, that's more than 60. You're either in one group or the other group. Well, it took me -5 minutes. It did not take you -5 minutes. That is a lie. So the probability of 60 minutes or longer is this area in red, and that's 25.14%. Okay. Now, what is the probability that it takes 35 to 50 minutes to cook dinner? So now I'm looking at a fairly specific region here. You can see here's 35 and here's 50, and I'm going to try to end up in that little region there. And let's see if I have a picture associated with that. 35 here, 50 here. So it's going to be kind of small, but we approach this problem in the same way. I'm going to try to make some z-scores. First, I find a z-score for 35. 35 minus 50. 50 is still the average amount of time, so 35 is a little bit less than that. Divide by 15, so I have -15 divided by 15, that's -1. Now, that's the first z-score. So what we do in this picture is we convert the 35, and instead we're moving it over to -1. Let's look at 50 minutes. I take 50, I subtract the mean, which is also 50, so I have 0 divided by 15, which is 0. So I convert the 50 here, which is right in the middle, to 0, which is right in the middle. So I'm mapping the 35 and the 50 to a different location on my standard normal distribution. Okay, so I do that. Am I done? No. Do I take -1 and subtract 0? No, those are not probabilities. They're descriptions of location. So I next find the probabilities associated with -1 and 0. So the plan is I'm going to find 0, I'm going to find -1, and I'm going to subtract the smaller probability from the larger probability. So let's try that out. I'm going to go to the z-table, and I'm going to find 0. 0.00, that's 0.5. Half the time it takes 50 minutes or less to cook dinner. Makes perfect sense, 50 is the mean. Okay, let's try to find -1. I go to the negative side of the z-table. There are two sides to the z-table. So here's -1.0. Okay, so that's the row that I want to be in. The column is 0.00. That's over here. So I'm in row -1.0, column 0.00, and I get 0.1587. Okay, so if we go back to these slides, everything to the left of -1 is 0.1587, and everything to the left of 0 is 0.5. So I just want to take the 0.1587 and subtract from 0.5, and I get 0.3413. 34.13% of the time, it takes between 35 and 50 minutes to cook dinner. That's based on the modeling assumption that I chose. Okay, so Excel can actually calculate probabilities associated with this z-score. We can use Excel to do some of these calculations for us. So we're going to use the function norm.dist. Let's try it out in Excel. Okay, let's open up a new workbook. Okay, here we are in Excel. And let's say I want to find the probability of more than 60 minutes. The idea, look up z-score, subtract from 1. Excel we're going to use norm.dist, subtract from 1. Okay, let's try it out. Equal norm.dist. X is the number that we're interested in. That's up here. X goes first. The mean is 50. The standard deviation is 15. Cumulative is everything up to 60. You can see that we get 0.7475. Not 0.7486 like we had. The difference is that Excel actually didn't round. Okay? So this is what we have here on this slide. What if I wanted to subtract from 1? I can type in equal 1 minus, and then I can just go back and do norm.dist 60, 50, 15 true, and I have 0.2525. This is the less than, this is the more than. What if I want to find the probability of between 35 and 50 minutes? The idea, look up two z-scores, subtract the smaller probability from the larger one. In Excel, we're going to use norm.dist twice, and we're going to subtract the smaller probability from the larger one. So the ideas are very symmetric. Let's try it out. Norm.dist. We do 50 first. That's the bigger one. And we're going to subtract 35. And we can do it all in one swoop. You can see we get the same thing that we had on the slides. Okay? What if I wanted to use the z-scores on their own? Use some z-scores. We can use norm.s.dist. Let's say I use norm.s.dist in the previous problem. I have a z of 0, and I subtract a z of minus 1. Same thing. The last type of problem that I want to look at is using the normal distribution to back out x. This is important because oftentimes in a business setting, you will not be given a specific probability-related problem to solve. Rather, you'll be given a top percentage that you want to be included in. So you want to finish in the top quarter of sales. You want to finish in the top half of your class. You want to finish in the top 10% of speeds running a half marathon. Whatever the case may be, you are looking for X, but you're not given a perfect range of where to look. You're just given some percent. So just to give you an example, suppose you're looking to hire someone for a sales position. They claim to be in the top quartile in their current job. They don't tell you the exact sales amount. So you tend to find a lot of these types of problems when negotiating over salary. They'll say we're offering something competitive with the industry average. And so what you're really trying to figure out is, hey, what's the industry average? And hey, what's a standard deviation of that average look like? Because they're going to offer me something a little below the average. How far below is competitive? And so this is the same type of problem. You work at a similar firm, so you know the average at your work is $12,500 a month with 4,500 standard deviation. So think of someone selling cars, moving between car dealers who has been recognized for being in the top 20% of sales. Well, what has that person sold at that dealership is really the question you would like to know, but they're not necessarily going to tell you because then they're committing to a level of productivity that they may not be able to match in their new environment. Okay, so they claim to be in the top quartile, the top 1/4, and the problem indicates that 75% are below some X. So just to take a look at the picture, it looks something like this. They are in this red. You're not exactly sure where the red is. You know that 12.5 is your number, and you're trying to convert that in some way to something that you can look up in the Z table. So when we have these types of problems, the strategy is to first look up a z-score that yields a probability close to 0.7500. I can't look up 25% because the z-table only looks up less than. So I know that being in the top quartile is that you do more than 75%, but unfortunately I can only look up less than. So we're going to look up a z-score that yields a probability close to 0.7500. The probability is a 4-digit number. Okay, so not very close. 0.0002, not very close. Getting closer, but still far. Getting closer, but still far. Closer, but still far. The negative side of the z-table only goes to probability of 0.5. So we go over to the positive side. 0.5, 0.5398. We're getting closer to 0.75. 0.5793, 0.6179, 0.6554, 0.6915, 0.7257. Okay. Here's 0.758, so we went too far. Let's go over. Okay. 0.7486 is close, as is 0.7517, and we can take either one. Either one. So you could use a z-score of 0.67 or a z-score of 0.68. Those would be fine as round estimates. Okay. Now let's go back. So I found a z-score. That's pretty close. I plug that z-score into the equation for x. So I know what the mean is. That's 12.5. I know what the standard deviation is. That's 4,500. And now I know a z-score. That's 0.67. So I use this to solve for x. And you can see in the calculator what I do is take 0.67 times 4,500. And then I add 12,500. And that's how I get this 15,515. I just cross-multiplied. So I use the probability to convert to the 0.67 first, and then I go back and put in 15,515. Now, Excel will do this for you with the norm.inf function. So the idea for this top quartile question was to use the z-table to find a z-score close to desired probability of 0.7500. Then use z-score to find x. Excel has a built-in function norm.inverse that will do this all in one step. So norm.inv, take the probability that you want, that's 0.75, take the mean, which is 12,500, take the standard deviation, and boom. Right there. And you can see that on this slide. I provide a screenshot of it, but you saw right there in the video how it works. We bothered to review the z-table for Econ 3406 because most problems are summarized as follows. You pick somebody out of the population randomly, and you're looking for the probability that an attribute is less than or equal to a certain number. You get a z-score. You look up a probability. We often do this in Stats 2 with samples. And so that's where we're going to end off today.